In this video, I'm going to tell you what the Higgs boson is and what three limitations of the standard model of particle physics are. The Higgs particle is that last particle, that yellow particle, in the standard model of particle physics. And it's a very interesting particle, and I'm going to cut right to the chase. What the Higgs particle is a concentration of energy in the Higgs field. What the Higgs field is a field that permeates the entire universe that concentrates around certain particles, and it gives those particles their mass. A metaphor often used here is that the Higgs field is like molasses, and other particles are like particles or waves shooting through the molasses and getting slowed down, and the more it's slowed down, the heavier that particle will become. So, to repeat in slightly different words, the Higgs field is the field that, through its interactions with what we think of as ordinary matter and a couple of the force particles, makes all the mass of the universe. Another way of coming about this, to make this slightly more intuitive, is to understand where we were coming from when Peter Higgs and others proposed the existence of the Higgs field. One of the things that's clear about the forces is that they have different ranges. Gravity is infinite, electromagnetism is infinite, but both the strong force and the weak force are not infinite. And one of the problems was that our theories prior to the discovery of the Higgs actually seemed to suggest that all forces should be infinite in range. And the question came, what was making it that the strong force and the weak force, which should be infinite, are not infinite? In fact, are very finite and only exist on a very short range. And it was in response to that and the realization that, according to our models, no particle should have mass at all, that the Higgs field was proposed. And the Higgs field was a place which would change this, would take these certain forces and certain particles and give them mass, and give certain particles more mass than others. So in other words, the Higgs field prefers certain particles over others, and the way you can tell which particle is preferred is just look at the size of the particle. Look at the range of a force, and you'll see that the smaller the range, the bigger the particle, the stronger the preference and the interaction of the Higgs field with that particle. And similarly for matter particles, you look at the heavier particles, more interaction with the Higgs field, lighter particles, less interaction. Massless particles, no interaction. Okay, so the Higgs field rounds out our view of the standard model of particle physics. We have our fermions, our matter particles, our bosons, our force particles or interaction particles, and our weird boson, the Higgs boson, which is responsible for giving all particles mass and for making the short-range forces of nature short-range instead of long-range. However, this model that we've spent the last 3 videos explicating is inadequate. And it's inadequate in 3 serious ways. The first problem is gravity's nowhere to be found. There's this blue graviton, but that's just a hypothetical particle. We haven't found it yet. And it's not just that we haven't found it yet. It's also that our theory for gravity is actually different than our quantum mechanical theory for the standard model of particle physics. Our theory of gravity is still the theory of relativity, is still Einstein's relativity. And that really bogs us down in classical physics rather than modern physics. So maybe there's something weird going on, and maybe our predictions for the graviton aren't going to pan out. And if that's true, if we don't find the graviton, that's going to lead to a lot of very justified head scratching. And this is going to be an inadequate recipe book for all of matter. But there are other reasons why this is an inadequate recipe book for all of matter. And that's that most of the energy/matter in the universe isn't accounted for. To be specific, 96% of all of the energy/matter in the universe is not accounted for by this model. Correspondingly, only 4% is. And the 96% that isn't is to be found 23% in dark matter and 73% in dark energy. But you'll notice that there's no dark matter particle in this model. This is a serious problem, again, because most of the mass energy of the universe is not accounted for by this model. However, when it comes to our local universe, and I really mean very local, smaller than our galaxy, before you start seeing any of the effects of dark matter, when it comes to that local universe, this actually covers it all, aside for gravity. Now that we've covered the standard model of particle physics and we fleshed out the limitations of this model, we can turn to the last two things of reality. 1, dark matter. 2, dark energy. I should mention for anyone going through this series that I left something out. I left out antimatter, but we're going to touch that once we start hitting the early universe. Till next time, when we talk about dark matter.